Good evening, all. I'm very delighted that many of you can join today, and it is very exciting day today to kick off our second session of OCTAVE Insight webinar series. My name is Dr. Rajitha Navaranna. I'll be the host for this evening. At OCTAVE, I'm working as a principal data scientist, where myself and DS team is responsible for creating high-impact data science projects for John Case Holding. So our team work with a very rich amount of data from several business domains, including retail, beverages, insurance, and hotel industry. We hope this will be an interesting session, and please feel free to share your comments, questions at the end of the presentation. We have a Q&A session at the end of our seminar. As you probably aware, Microsoft is sponsoring a giveaway at each webinar in this series. And the winner of the previous webinar in data engineering is Tilini Patirana. Congratulations, Tilini. So let's move on to our session today. So let me introduce the speaker for the evening, Dr. Paul Beaumont. Paul is a principal data scientist at OCTAVE, a McKinsey company in Singapore, where Paul and his team working with clients across Southeast Asia on a variety of descriptive, predictive, and prescriptive problems, specializing heavily in causal inference and Bayesian networks. So he holds a PhD in computer science and a master's and a bachelor's in mathematics from Imperial College, London. So it's our pleasure to have you, Paul, today for our second session of OCTAVE Insight webinar. Paul, it's over to you to conduct the session. Thanks.
Cool. Thank you very much. Thanks, Rajitha, for the introduction. Good evening, everyone. Thank you for joining. As Rajitha introduced, I'm going to be talking today primarily about causal inference. But before we kind of like deep dive into that, I thought we'd start slightly higher level and we start off talking about machine learning as a whole. When we talk about machine learning, or at least supervised machine learning, there's no single way to kind of cut this into to describe or dissect all the different types of models. Lots of different dimensions to it. One particularly popular way is to think about things in terms of being a predictive, descriptive, or prescriptive model. Each of these all focus around the same equation. So y equals f of x, where y is our target variable, f is the function that binds our features, and x are the features themselves. It's just that for each of these different types of models, there's a bit of a different focus. So for a predictive model, where we're interested in finding out more about the target, we really care about the y. For a descriptive model, we don't necessarily care about predictive performance, but we care more about understanding the relationships between, say, the features and the targets. So we care more about the f. And then for the prescriptive case, we're actually trying to find an optimum quite often. So this is kind of like finding the optimal features or kind of optimizing the x. So this is kind of like one way of splitting kind of supervised learning up into three different buckets and categories. But when we're doing data science, essentially all we're trying to do every single time is find like the right model. And again, this is like a very difficult thing to sort of put your finger on and sort of clearly define. But kind of like, again, one common way is to think about how well does our model perform on data that's not seen before? So does our model generalize? So is our model actually learning how to generalize, or is it just remembering data that we've seen? And again, there's lots of different trade-offs. Data science is seemingly all about trade-offs. But kind of some common trade-offs would be around, say, the model complexity versus the actual performance that we can achieve, so the prediction error. And obviously, kind of, imagine that we have some sort of data generating process, which is the green line in each of these, and we observe certain bits of this data generating process. So these are just the blue dots that we have samples of. Then when we're trying to pick our model, so say the red line, if we were to go super simple, like in the A box here, so kind of the model complexity would be very low, we'd expect our model to basically not perform very well at all, either on the data that it's seen before or the data or unseen data. Then as we kind of get a slightly more complicated model, maybe we're able to fit to the data slightly better, our performance improves, our errors go down, the model is slightly more complex. To go to I mean, there is no model is perfect, But essentially what we're trying to find is a good balance between data that we've seen before. So we perform very well in terms of errors on our training sample, but we also perform well on data that we've not seen before. So C is sort of like the optimal sort of model that we're looking for. And then just to finish off and go to the next extreme. There are certain instances where the models can get too complicated, and actually it ends up just overfitting to the data. So D would be an example, which is again a very bad model, right? Because whilst it may fit very, very well to each of these blue points, we can see it actually looks nothing like the true data underlying it, so the green distribution. So these are some of the trade-offs, some of the decisions that have to be made, and this is all kind of a little bit experimental in some ways, and subject to kind of lots of different hyperparameters, lots of different model choices, in fact. But it's just one dimension. Another dimension that we sometimes have to think about is, how is the model going to be used? Who is going to be using the model, and kind of what do they need? Are we going to be doing this in an environment where we need to be particularly conscious of algorithmic fairness? Maybe there's some historical bias in the data that's been collected, and what we don't want to happen is we don't want our models to essentially just reflect the same historical biases that exist in the data. Maybe our model needs to be particularly interpretable, because we need to have to be able to explain the recommendations that are coming out of our model. Maybe kind of, that this is a model that's going into production, and we need to be confident that over time the model will continue to perform. Maybe there's some very slow sort of data set shift where the data is slowly changing over time, which is very realistic as well, right? The real world does not stay constant, data does not stay constant. So maybe we have to really care about the ongoing performance in the future. The blue box, which I've obviously skipped over slightly, is my favorite topic, and it's basically where my PhD was focused. And this is on causal inference side as well. So kind of, does our model make causal sense? And each of these areas are all sort of very active research areas, things that we actively work on at Quantum Black, the company that I work for. And so today we're going to do a bit of a deep dive into causal inference. There are definitely some relationships with other areas as well, sort of fairness, bias, explainability, causal inference, for sure, all sort of related. So this evening, though, rather than me just always talking all the time, I'm going to try and make it a little bit interactive. And so kind of I'm going to ask two questions on the next two slides, just to hear your thoughts and see if you guys can figure out what the problem is, what's going on as well. So I've got two questions. Please, for this, just use the Q&A feature. So you should be able to see, hopefully at the bottom of the screen, I think, there should be like a Q&A button. So normally you would use it to ask me questions, right? But I'm asking you the questions. So please try and use it to offer some answers. And so essentially my first question is, what's going on here, right? So when we do a descriptive or an explanatory model, we'd sort of expect this model to make causal sense before we trust it. So, if we look at the graph on the left-hand side, you'll see that the x-axis is the severity of damage that is observed from a fire. And on the y-axis is the number of firefighters that actually attended that fire. So, lower number of firefighters, less damage, higher number of firefighters, more damage. So the question is, the implication from this, should we get rid of firefighters? Reducing the number of firefighters reduces the severity of damage. On the right-hand side, we have another graph. So this graph here is kind of on the x-axis. We've got the sales of hot drinks and of sunburn cases. So kind of the dark blue line is sunburn cases, and the light blue line is hot drink sales. And as you can see here, as the number of sunburn cases goes up, the number of hot drinks sales goes down. So the question is, do hot drinks, if we have lots of hot drinks, do they cure sunburn? So my question to everyone here is, what's going on? Is there a causal link that we could use and we could, make some inference off of? So I'm just gonna have a see. Okay, one person responded so far. Any other thoughts from anybody who's listening? Okay, so we've got another one coming. Ah, okay. Someone else's. So a third. I really like the third solution. Cool. Okay, guys. So there's a few things that people are talking about here. People talking about correlation, not causation, which would fully agree. As we all know, correlation doesn't guarantee causality. The response that I really like, I'm just trying to find it again. The more the severity of the fire, the more firefighters are needed to work on it. For the second one, there's no causal link directly. Probably there's a third factor causing these two. I really, really like this response. And I fully agree as well, right? So kind of the point that I was trying to make was basically that maybe it is spurious, right? So maybe it is due to something that's a spurious correlation, and it's definitely not causation. But I think what's probably going on here, right, is that as someone pointed out, there is something else driving these things. There's what we know in data science as a confounder. So actually, kind of probably the number of firefighters and the severity of the damage is probably both driven by how bad the fire is, right? You don't send a lot of firefighters to a really small fire, and so therefore, you get very little damage. And similarly, you send a lot of firefighters to a really big fire, and they may try their best, but you're probably not going to save everything. There may be still quite severe damage. And then similarly, kind of, maybe temperature is driving the graph on the right, where kind of, as the sun comes out and the temperature goes up, number of sunburn cases goes up as well, and maybe people drink slightly less hot drinks. Maybe people switch to cold drinks instead. So again, there's this confounder of temperature going on. Maybe let me give you slightly slightly silly examples, I guess, in some ways. I have a second question for everyone. So this time, imagine that we control the data that is being generated. So you can think of it either as a graph, or you can think of it as a system of equations, right? So kind of where R and A, so R is the country of residence, A is age. Let's just imagine they're just normal distributions of something. I know that a normal distribution of country of residence doesn't really make much sense, but just bear with me a little bit. And then C, say, is dependent on R and A plus some other noise. T, exposure to sun, is also kind of, it's dependent, it's driven by R plus some noise. Y, a person's kind of, susceptibility to an illness is driven by both T and A. Okay, so my question this time is, okay, which of these two models are better? So in the first model, so we're interested basically on kind of understanding a person's susceptibility to an illness. In the first model, we only give it one variable. We only give it T. In the second model, we give it more variables. We give it T and we give it C. Which of these two models here? So this is just like a linear regression, right? Just using OLS linear regression. We have our independent variables here. We have our dependent variable Y. Which of these leads to the better model? So again, just like the first question, just send in your thoughts over the Q&A. Don't have anything yet from anybody. Oh, okay. First question. Oh, okay. Oh, I like that answer. Depends on the problem. In data science, everything is it depends a little bit. I know it's called data science, isn't it? But it sometimes can be a little bit fluffy. Okay, we've got a mixture of answers. Some people think the second model. Some people think the first model. Okay, in the interest of time, let me just share my thoughts on this and keep going a little bit. So, I mean, the way that we would normally assess a model, right, is, we'd look at how it performs error metrics wise. So, like RMSE, very common metric, we're always trying to reduce the RMSE, right? R squared, another common metric, we're normally trying to improve the R squared. So kind of like a lower RMSE in the second model, a higher R squared as well in the second model. So by all sort of standard metrics, the second model would be the better one. But if you look at the coefficients that's going on here, the relationship between t and y in the first model is like 0.99984. The relationship between t and y, so through the coefficient in the second model, is -1. If we look at the true data generating process, we know that actually the true relationship between t and y is +1. So actually kind of, the first model, even though it performs worse by standard metrics, is closer to the true data generating process. And again, and this is a bit of a paradox. So this is known as Simpson's paradox. And the reason why this happens and why essentially this second model doesn't pick up on this, by all intents and purposes, it kind of fits the variation. It can fit to the data better. But actually, what's happening is that it's ignoring the causal relationship between t and y. The causal relationship here is a multiplicative factor of 1, right? A coefficient of 1. But this has been completely ignored, and that's because quite a lot of machine learning, in fact, all of machine learning basically, doesn't really care about causation. It only really cares about correlation. I actually saw this on my LinkedIn feed a couple of weeks ago, so I had to steal it and put it into the deck. Basically, we've got two guys pushing a van along. One guy, he's pushing the side of the van, but from on top of the van, right? So kind of he's correlating, but he's definitely not causing this van to move. And so this is a big problem, right? Because machine learning is not capable of picking up causation on its own. And this is when we're working with data. Most of the data that we work with in data science tends to be observational data. So this is data that has been kind of collected before we actually started doing our analysis. If we're very, very, very lucky, we can get something that's known as randomized control trial data. And this is actually one way to account for causality, because we can essentially offset all of our confounders, so that they're known as unconfounded by design. And so we see things like RCTs in clinical trials. So all of these COVID vaccines that are being tested at the minute, they're going through randomized control trials. They're like double-blind tests where we can essentially control for these factors that could be interfering with the causal direction. However, all the data in the world doesn't look like this. And in fact, it's actually very expensive quite often to collect this sort of data. So we often end up with very small data sets, potentially limited generalizability. So because they're small as well. There may be some ethical concerns as well. So kind of depends what you're testing, right? But you can imagine if you know it's going to be a bad outcome for somebody, maybe there's some ethics about actually setting up a trial that's going to lead to a bad outcome for somebody. On the flip side, so observational data, which is just data that exists, historically been collected. The problem is that we weren't asking the research question when it was being collected, so it's not unconfounded. It is definitely, it's got biases in the data. However, on the flip side, there's a lot of it. And because there's a lot of it, it's what we kind of tend to work with and what we tend to use. So pros and cons to both, for sure. It just so happens that probably like 99% of the data that we have to work with is observational. So whilst if we got to control the data generating process, we may not need to do anything. We may be able to just set up an RCT. Really, realistically, we have to find other ways of being able to handle causation in our modeling. And I'm not going to claim to you today that we've solved a way to work with observational data and assess true causation from historical data. It's not true, right? It just definitely doesn't happen. However, there are some techniques that kind of we can apply to get to a better solution, better than just blindly going into it. And so this is where something that's known as Bayesian networks come along. So Bayesian networks are essentially kind of a graphical form of modeling. And kind of they have different sets of assumptions to more traditional things. So kind of more traditional sort of models like linear regressions, decision trees, etc. They often just think of the relationship between the features and the target. They don't necessarily take into account the relationship between the features, which is obviously not actually quite true in the real world situation, right? So kind of this, if you think about the graph that I just showed you, obviously a Bayesian network, because it's graph based, can basically recover the same graph, and we know that this is a true reflection of the data generating process, right? Because we control the data generating process. The best that we can do, though, in a linear regression, I mean, yes, we can make interaction terms, etc., but basically all of the features are acting directly on the target, or have been modeled to act directly on the target, which is not true, right? So C does not actually act directly on the target. Neither, for that sake, does R. R acts through T. So there are different assumptions that go into a linear regression, to a Bayesian network. Linear regressions assume that all of the features are independent, which obviously is not always perfectly true. We try to get rid of multicollinearity as much as we can, but all of our features are not truly independent from each other. Bayesian networks have different assumptions where maybe you need some more domain expertise to kind of like fit the direction of the edges. So again, some pros and cons. And maybe just to do a bit more of a deep dive on a Bayesian network, just to talk you through some of the terms. Essentially, we think about it in terms of nodes and edges. So the node represents all the different variables that there are to model with, and there's actually no distinction in a Bayesian network between the target and the feature. The target is just a node as well. Okay, so like we as data scientists, we have a particular node that we're interested in, but to a Bayesian network, it's just a graph. The edges, though, have to be directed and they have to be acyclic. And by acyclic, I basically mean we can't introduce a loop. So we can't have absences goes to grade, grade goes to internet, internet goes to absences, etc. That's not allowed inside a Bayesian network. So everything has to be directed, so there has to be an arrowhead. And when we learn a Bayesian network, we can't actually learn the true causal direction. The idea is that these edges represent the causal direction. So that internet, so this example here now, instead of being about illnesses and temperatures and cars, etc., this example here is about a student and what grade they get based on the time that they spend on the internet, their absences from school, where they live, how many previous failures they've got, family, parental status, etc. All of these things affecting their college grade, basically. So the causal direction, the idea or the hypothesis is that internet drives, so the amount of time that you spend on the internet drives your grade. And we don't get to see from this whether it's a positive effect or whether it's a negative effect. We don't see that from just the graph. We just see that this is the causal direction. But when we learn this graph, we don't actually learn the causal direction. We actually need a domain expert's input in order to make sure that these edges go the right way around. So we can learn the structure, we can learn the edge, but we have to use a domain expert to help fit the direction. So again, that's another, it's a bit of a con to using a Bayesian network. A linear regression, we don't have to get a domain expert to come in and help us fit the linear regression, right? We can just use OLS and it will help find the coefficients. For a Bayesian network, though, in order to get it acting causally in some sense, so a BN on its own is not inherently causal, but with a domain expert's view, it can be made to be causal. So they do need a little bit of extra help. But there's some cool things that we can do with them as well. So once we've actually learned this model, then similar to a linear regression, the equivalent in a linear regression, I guess, of like fitting the coefficients, is we fit the probabilities. So then we essentially find conditional probability distributions for each of these nodes, which tells us, okay, what is the effect of this node on another? Okay, so how much does changing this impact this? And the cool thing that we can do then from a causal inference perspective is we can both observe things and we can intervene. And this is one of the key kind of like concepts in causal inference, is that we want to be able to make, we want to ask counterfactual questions. Counterfactual questions are basically asking things from the data that didn't actually happen. And so like, there's very limited information to go on. And so we can do counterfactuals or interventions. Everything in data science has like two different names for it. So kind of by intervention or counterfactual, it basically means the same thing. And because they're Bayesian, so basically a Bayesian network follows like a complicated form of Bayes' rule where we get to update the probabilities. So as I'm sure you guys know, kind of like, in Bayes' rule, we have a prior and we have a posterior that updates as we get more evidence. And what this basically means is that we can have an initial view of the probability distribution at a particular node. So here, imagine that we're interested in node C. Now, because C is driven by A and it's driven by B, C is essentially conditioned on the probabilities that exist inside A and B. D is driven by B, but has no impact in C, right? If we condition, though, in a Bayesian way on D, we've observed something, we've seen something. And because we've seen something, we learn something about the other probabilities. Okay, so kind of like I've observed evidence at D. When I update it, it tells me more information about B. And because B is then updated, it then means that because C is downstream of B, that C also gets updated. Okay, we've learned more information about the real world. Vice versa, though, finding the counterfactual or intervening is very different. If I do something to D, it doesn't mean I've necessarily done anything to B. It means that I've broken the relationship between B and D, because now what I've done to D is because of an action that I have taken, not anything to do with the fact that I've learned any more information about A, B, or C. So this is actually a different situation, because now, in this instance, the probability of C does not change, because D is downstream of B, and it's something that I've intervened on. So a Bayesian network behaves differently in this situation. Similarly, let's imagine that we do something to B, right? Okay, in this instance, it tells me nothing extra about A, because I've broken the relationship with A, and I've just affected things which are downstream of B. So I've made an action, and I've had an impact, but only in the causal direction. And this sort of counterfactual analysis. I won't go through them all, right? You can see for yourself. It gets a little bit complicated. You know, sometimes it's the same thing if I was to do it on A, but this is very different to what we can do in the linear regression. We can't do this sort of analysis. So this makes like Bayesian networks very, very popular for asking these sorts of causal questions. And so kind of one thing that, oh, I do apologize, my font has not gone very well. This is meant to say pip install causal next. But essentially kind of like there's a package out here, which actually Quantum Black, my company, we developed to work with Bayesian networks. So, you know, this is a free open source package that we built for working with Bayesian networks. And it's something that essentially allows you to do all the steps that I've just talked about. So it allows you to learn the structure. So learn this graph, allows you to kind of edit this graph with the domain expert's input, allows you to visualize it, so you actually get the picture. You can, you know, it is at the end of the day meant to be an interpretable and you know, explainable method. And then it allows you to ask questions of it. So, you know, fit the probabilities, so do the likelihood estimation, as well as answer these questions. So to kind of go into it and say, okay, now I've learned my graph, I've learned my probabilities, let's use it and let's ask some questions. So if you guys are interested to try out a Bayesian network, it is relatively simple to do in Python, thanks to this package. I'm just going to finish off. I think I've only got a few minutes left. I'm just going to show you kind of some real world examples of how we would use this at Quantum Black. So, you know, this is a slightly bigger graph. And essentially what we did for this data was we were interested in working with a pharmaceutical company who wanted to understand all of the different comorbidities that affected a disease that they were studying. So they were studying coronary artery disease, and they wanted to understand kind of, you know, comorbidities of the disease, but also kind of like patient demographic factors. So kind of, you know, maybe kind of whether the patient had was obese, where they lived, their lifestyle factors, and what sort of impact all of these comorbidities, as well as the, oops, sorry, that wasn't my intention, all of these different comorbidities had on essentially a heart attack. So MI, which is our target variable here. So remember, it's just a node in the graph, right? So kind of like, as far as a Bayesian network cares, it's just a node. And MI is a myocardial infarction, which is basically just a heart attack. And so we basically built this network off of insurance claim data, where we looked at all these different diseases. We mapped the relationships by learning the structure of the network. And then we were able to kind of, you know, do some cool things where we were able to look at the sensitivity. So because we also learned the probabilities that go behind these nodes, we were able to answer questions like, okay, how strong is the relationship between, say, well, this example here, right, is long-term use of aspirin and whether a patient needs to be hospitalized. Is this a big factor to take into account? So kind of, you know, you can imagine that the sorts of analyses you can then do on top of that is essentially like, okay, say I want to make an intervention or I want to make a change. There's very, very little point making a change where there is only a weak relationship. Because if there's a weak relationship and it's only going to change the outcome a little bit, then maybe it's not the thing that you want to focus on. Maybe you want to focus on something which is far more important for changing the outcome. So this is the sort of kind of analysis that we'd be able to come out with. It is highly illustrative, I do want to say. I think there's a lot of things in here which we had to change for example purposes, so we couldn't show you the real graph that we actually came up with. So it is a little bit of a demo more than anything else, but hopefully gives you a picture of the sorts of very quick and easy view. It's very explainable, right, that you can get of the data. The thing that you can do on top of it, so this goes back to the queries and the interventions, is basically we can then create stories. So we can kind of like map out a patient's journey through time. So essentially maybe something like, we started off with a patient who was a smoker. They had a relatively high BMI. They were, 50, so kind of like middle-aged, and they had a disease. Then we can kind of see, okay, how does a patient's risk profile change? So they, at 5.1%, they're already above the baseline risk. But how does their risk profile change as their comorbidities change, as other features change in the Bayesian network, in the graph? So you can see that essentially what we're doing is we are observing new things. We're imagining that we've observed that, Mrs. Smith has grown older. She's developed some symptoms of heart failure. We've not done anything to her, right? So we've not intervened. We've just observed something, and the Bayesian network is updated to give us a new patient risk profile. At the same time, maybe we do intervene. So we observe that she's got older, but we intervene and we make some lifestyle changes. She stops smoking. She loses some weight, so her BMI goes down. So when we've done this sort of analysis, it's different to observing it, and it has a different impact on it would give us a different result if it was only an observational thing, but we get to see the impact of that intervention. So these are the sorts of things that we can do with a BN. I'm not going to claim that a BN is the only way to do these things. There are lots of other methods out there. I'm a little bit biased in some ways because my PhD is in Bayesian networks, and so kind of like it's what I'm most familiar with. It's what I've worked with for the last well, 6-7 years or so. I think the takeaways that I just wanted to finish off with are essentially that causal inference is a very, very important topic for data science. We can use our models for making interventions, for making decisions, and if we're going to share them with our stakeholders, then essentially they want to trust them, and they need to make causal sense to the end user as well. Unfortunately, a lot of data in the real world is going to be observational, and so kind of, it's not going to be a clear-cut answer as to, it will be confounded, there will be biases. But there are some methods that are able to help us identify causal relationships. So kind of, there are a few exploratory data analysis techniques that I didn't have time to talk about today that you can apply, and it will give you some sense. You can look at some statistics, but it's not the true causal direction. However, domain experts can help work with us, work with data scientists, and work, say, using a Bayesian network, because it's the sort of model that is a hybrid approach between learning using data and domain input. We can capture some of this causal relationship. So I think they're the key points and takeaways that I wanted to share from my side. I think, Rajita, am I handing over to you to talk through the giveaway slides?
You can take it.
I can take it. Okay, cool, awesome. So I think similar to the last meetup, there is another giveaway that was mentioned at the beginning, and so there's 2 questions for this giveaway. So I think the ask is to please send your answers to this. So this time it's not doing it on the Q&A. Instead, this time it's sending it to the email address here. But essentially, question 1 is, which of the following statements are true? And so there may be more than one right answer. In fact, there's definitely more than one right answer. So which of these are true? Machine learning techniques care about correlation, not causation. Bayesian networks are inherently causal. Randomized control trials are unconfounded by design. And domain input is needed to make a Bayesian network a causal graph. So this is the first question. I'll just pause here for a second just to let people read through again. Please feel free, take a screenshot or something if you think that would be helpful. And then we've got 4 different possible answers. So send question 1 and then either A, B, C, D with your answer to here. I'll give 10 more seconds and then I'll go on to the next slide, which has got question 2. So give just a few more seconds. Feel free to take a screenshot or something like that. So then question 2 is, which of the following statements are true? So this is going back to the example graph that we had earlier. So this is about country of residence, type of car owned, age, illness, and exposure to sun. I apologize for the noise if you could hear that in the background. So in Singapore, I live right next to the cruise ships. So one of the cruise ships was just blaring its horn. Sorry if you could hear that. So this is back to the graph that we had. And the question is again, which of the following statements are true? So 1, C is a child, so a child node of R. 2, C drives Y. 3, intervening on C would impact Y. And 4, observing something about C would impact Y. And again, kind of like 4 different answers, A, B, C, D. So yeah, so they asked us to basically send your answers to question 1 and to question 2 together to this email address. And with that, again, take a screenshot if you think it would be helpful. I will, I think, pass back to Rajitha.
Thank you, Paul, for very interesting insights. We are open for a few questions from the audience. So feel free to send questions or comments in QA feature. So we have a few questions actually. Paul, if you take some topics in statistics inference, such as sampling, hypothesis, like p-values, t-tests, like many of data scientists are familiar with these kind of techniques. I mean, if you take these kind of examples, what we do is, so we have like a sample of data or some observation, and we hope this particular sample of data will be not too far from the true number if you observe the entire spectrum of data, right? So, but in statistical inferences, what we do is from the data we have, we try to learn about the data which we don't have, but we have the feasibility that we can go and collect the data, right? So that's more like the statistical inferences. We are probably like if we have the entire data spectrum, probably we don't need like statistical inferences. But from my experience, what I saw in causal inferences, what we try to do is how can we use the data we have to learn something impossible to get done, right? So we have the fundamental problem like in statistical inferences, if you have like more data, we can come to like a very closer answer from the sample data. But in the causal inferences, that particular problem is still exists, right? Because it's difficult to have such a data.
Yeah, I mean,
So,
like
am I correct in saying that that's the fundamental problem in causal inference?
Yeah, I think what you're saying basically is like the counterfactual is the fundamental problem, right? Like it's something that we've not necessarily seen before. It's against the history. It's against the truth that has been observed. So yeah, I think that missing data and trying to account for that is essentially the crux of what we're trying to do. I mean, without obviously deferring to RCTs, it sounds as though from the way you started to describe it, it sounds as though sometimes you have the ability to go and collect data. I think that's also a fantastic way as well, right? If you can essentially running an experiment is very similar to like setting up your own RCT. Hopefully, when people do their experiment design, they would design it in such a way that it is unconfounded as well, right? So you may not be able to get to the same sort of level of confidence that people who run clinical trials do in terms of like double-blind studies and things like this. But yeah, if you have the ability to go collect data, then that's that's way better and similar level to like an RCT. Unfortunately, I mean, like in the job that I do, I don't actually get I don't actually get to do that, unfortunately, sometimes. So yeah, I'm stuck with working with observational data for most of the time.
Oh, okay. I have like a couple of questions too. Like, how does causal inference links to the other topics such as explainability, like fairness, those kind of areas?
Yeah, no, fair, good question, Chris. I mean, they're all intertwined. So I guess kind of causal inference is inherently trying to explain what's going on to someone as well. So there's obviously lots of strong relationships then with like explainable AI. Explainable AI though, goes beyond just what causal inference will focus on, because it tries to look at the black box models, etc. So there's only partial overlap, I'd say. But definitely, kind of like interpretable by design. I'd sort of call a Bayesian network a interpretable by design method, and by interpretable, it therefore means that it's explainable. So it is just one type of explainable model, as well as being a model that can be in some ways made to be causal. Then the fairness bias overlap. So kind of, again, I guess the fairness bias thing comes back to the counterfactual point as well, right? Because kind of, if you've got a bias in your data, it's because you maybe haven't collected it previously. Maybe your data, your observational data is biased. And so kind of, there's lots of work in fairness work to try and account for that in learning in the model, to make sure that the model doesn't learn the same biases that we have in society. And then kind of like the causal inference attacks it from this slightly different way of trying to find this counterfactual action. So I guess fairness approach more often than not tries to adjust the model to not learn the same biases, whereas causal inference says, okay, we accept the biases, but we try to learn what was not there. I'm not sure if that made any sense, but kind of, I think that the short answer is kind of a lot of overlap and lots of intertwining.
Yeah, thanks for it's quite interesting. I mean, most of the data scientists, they are going after the lot of data, right? So like, if you take like many machine learning projects or even data science projects, they want a huge number of data. So a lot of data is very time sensitive. Can we apply Bayesian networks in here, like when you have such a data which is time sensitive?
Yeah, you can, and you can do it in two different ways. So you can either just use a plain vanilla Bayesian network where you make sure that your edges respect time. So kind of you could inherently capture time in your variables, in your nodes, and then kind of that you just make sure that that the edges don't go against time, because that would be anti-causal. So that's one way to do it, and I've definitely done it that way before. The other way to do it would be to use what's known as a dynamic Bayesian network. So dynamic Bayesian network is basically just the temporal extension to a Bayesian network. Yeah, so that's something that we've been working on relatively recently, actually, at QB, because we published a paper on structural learning for dynamic Bayesian networks. So yeah, I think the dynamic Bayesian network, the drawback though is you do need a lot more data. Like with a BN, you can get away with far less, but for a DBN, you actually need quite a bit of data to learn it well.
Okay, so that's what from your past experience you realized that those are the drawbacks of using Bayesian networks.
Yeah, well, I mean, I guess there's probably a few other drawbacks as well, right? Yeah. I mean, they're very good in some ways, but they, for instance, I mean, they weren't used for a long time because they were very, very difficult to learn the structures of. So I mean, BNs have been around since like 1980. They're designed by this, or they were invented by this guy called Judea Pearl, and they basically no one used them for a very, very, very long time, and because it was very difficult to learn the structure. It's very, very expensive computationally. But then kind of like a couple of years ago, there was a guy called Byron Aragam, I think his surname is. But he basically came up with this new method that allows you to far, far, far faster and far better learn the structure of a network. And since then, kind of like, I mean, that's when we basically started designing causal nets at QB, and when we developed that package, because it then became actually feasible to learn the structure. There's some other drawbacks as well, but I mean, so the way that we work with them, at least, we actually, I didn't go into a lot of detail on this, but we, in order to fit the probability distribution at each of the nodes, you can either do one of two things. You can either assume that the data is normally distributed, or you can discretize the data so that you actually get kind of discrete conditional probability distributions at each of the nodes. And so we do the latter. We discretize everything. This is obviously fine if you've got lots of categorical data because you're not throwing away any information. But if you have lots of continuous data, then another drawback is potentially that you do lose some of the granularity when you do the bucketing, when you do the discretization. So yeah, I guess that's two drawbacks, but everything is a trade-off, I guess.
Yeah. So just one question similar to Bayesian network drawbacks. So you worked in academic for like probably more than 5 years. So then you moved to industry to work on Bayesian networks. Did you see like any difference when you started to work on a very theoretical mathematics and when you started to apply those concepts for real world application? Did you see any challenges, and what are the bottlenecks you had when you started to apply these the concepts for real world applications? What I feel, and most of the data scientists, they actually go with like traditional linear regression and these kind of models, so they are not really looking to that causal inference Bayesian networks models. So did you see like any challenges?
Yes. I mean, I think I've got two thoughts on that. First is that I think QB actually only hired me because of my Bayesian network background. They basically wanted to expand into using more and more Bayesian networks. So I think I was brought in because of that, but in some ways. But then the other bit is that I was lucky enough during my PhD to do it with industry. So kind of like I worked for the UK's Ministry of Defence, kind of basically whilst at Imperial, kind of on trying to build mathematical models for nuclear weapon disarmament. So kind of like not the building of nuclear weapons, but the getting rid of nuclear weapons. And so basically, how do we build models where we they do verification regimes between countries where, I don't know, kind of like the UK will go to the US and they will do an inspection on kind of like what their weapon systems are, etc. And then the US will go somewhere else, and kind of maybe other countries actually will all move around and they will inspect each other, but they're not allowed to leak information that may give the other country too much of an advantage, and so that they have lots of information barriers to stop this from happening. And so essentially inherently we've got a situation where we don't have complete data and we don't know the full picture. We're missing the data, and we want to use a Bayesian. And so the idea was that, can we use a Bayesian network to essentially do the counterfactual and fill in that missing data? That was like the rough idea. And so kind of like doing that with an industry sponsor for 3 years then meant that I think the transition to working in proper industry was a little bit easier. Yeah, I guess there were other changes which were probably bigger, more about the pace of work than anything else, rather than the switch from theoretical. That was probably the bigger difference.
I mean, very interesting, very interesting. We have a few questions from the audience as well, so maybe I can go through a couple of questions. So one is, what does causal analysis not going to answer?
What is it not going to answer? Good question. So I mean, like things like this, right? They're not highly predictive. I wouldn't use this in a situation where I want to make highly performant predictions, right? It's not a black box technique. Things like ensemble methods, neural networks, etc. will probably be able to find more. They will be probably unintuitive, sometimes patterns in the data. But if you don't necessarily care about fundamentally, if you don't care about the causality so much, you're just looking at like pattern recognition, then causal inference, causal analysis like this is not going to help. And similarly, kind of things around like image processing, video processing, etc. Anything more complicated like this, at least I'm not aware of anything. There may be. I mean, it's a constantly moving field as well. I should also kind of like caveat. I'm not going to claim to know absolutely everything about the field, yeah, I think kind of once you go into like predictive stuff like that, then the ability for a BN to keep up with something like an ensemble method or neural nets, very quite limited.
Okay, thanks. I mean, similar question. How do I know when to use causal inference? Like any key parameters which help me to decide for a given data science project or problem? So like how can I know? Okay, for this particular problem, I should use causal inference.
Yeah, I mean, I think fundamentally, like if your model is going to be used to make like an intervention or a decision, or where you want to maybe kind of like quantify the impact of a decision being made, then it's a very good time to use causal inference. As we saw, right? And I know the example that I showed was like very extreme, but
yes.
as I showed that, just using like the simple linear regression, you've got exactly the opposite of the true data generating process, where I had a +1 coefficient and a -1 coefficient. So kind of, and if you were to make a decision on the back of that, your analysis of what was likely going to happen would have been very, very wrong, right? So I think kind of like those sorts of situations are like a no-brainer to using causal inference. Yeah, I think kind of it's good practice to be, even if you don't decide to use a Bayesian network in your analyses, it's good practice to be aware of these things, like and be wary of confounders which may affect the results in your models. Even if you're using a linear regression, you're using something else, and you see something that's spurious, it's good to know that maybe this is a confounder. Maybe I should be removing this from my model, or I should be using a different model that's able to handle this. Something like that.
Yeah, interesting. Couple of questions like have you used Bayesian networks to analyze COVID-19 data? Do you had any project with COVID-19 data?
So I haven't personally, but I have. I mean, so I supervised a guy who was working on something semi-related. He was working on the impact of working from home during COVID. So it was more like based on. So like essentially, actually, McKinsey did it internally. So we did like a survey of the people's happiness of in the new normal of working from home quite a lot. And so they did a Bayesian network analysis on that. It's a long time. I say it's a long time ago. It's a few months ago now. I can't remember too much, but yeah. So I think kind of it wasn't huge amounts of data. It was a relatively small sample, and there weren't too many nodes. It was very simplistic method. But I think they probably published it, and I think it's probably on McKinsey's website somewhere. But yeah, that's the only data that I've worked with for COVID.
Just one question for that, like what real world problems have you solved using Bayesian network?
Yeah, so I used it on a few different use cases. I mean, firstly was my PhD, right? So kind of like working for the decision support there. That was the first. We've applied it in a couple of different domains. So ones that I've done personally myself have been in pharmaceuticals, where we were looking to. So in fact, the example that I showed, right, as well, kind of earlier. But we've done that a couple of different times in a couple of different analyses. Another time that we've actually done it with financial institutions, with banks, where they've been looking to understand what drives the effectiveness of their sales force. So basically, we took the bank's data and we looked at what was the relationship between what the sales force was doing to sell new products to customers and the impact that they were having. So kind of, was the relationship manager, was the sales force calling the customer? Were they emailing them? Were they seeing them face to face? Were they a very specialist? Were they located far from the customer? Were they very close? So lots of different things that would potentially drive the impact. And we essentially did a Bayesian network to understand, okay, if you were to stop calling this type of customer and just email them instead, and if you were to start meeting this type of customer and stop meeting this type of customer, you could change the impact because of how the customers were essentially predicted to respond to different types of interactions. So we did it for that as well, in order to essentially propose changes to their business model and how they were working.
Oh, okay, cool. We have a couple of questions about the Python package. First one. What is the Python package we can use for Bayesian networks?
Yeah, there are other ones, right? I'm not saying that this is the only one, but yeah, I apologize for the font, sorry, but this is just Causal Next, so CAUSALNEX. So you can just pip install it. This is actually built on top of a couple of other packages. So it's built on top of a package which is known as PGMPY, which is a probabilistic graphical models Python package. The reason why, and you can just use Bayesian networks using PGMPY, but it doesn't support the more advanced structure learning, and it doesn't support the more advanced counterfactual analysis. So basically what we did was we built on top of this, and we brought in the counterfactual analysis and the structure learning. So the guy that I mentioned earlier, so I mentioned earlier that Bayesian networks weren't used for a long time because it was very difficult to learn the structure. The algorithm that kind of changed all of this is known as no-tiers, so the no-tiers algorithm. So this is in our repo, it's in our package, and yeah, so we use this for doing the structure learning, and then yeah, the counterfactual analysis bit is just this basically this bit. But yeah, you could just use PGMPY directly. Microsoft also have a package known as DoY. So DoY isn't inherently necessarily about Bayesian networks, but it is a counterfactual package. And so I know kind of people do use that to do counterfactual analysis, but not specifically Bayesian network related.
So how do you generate the network structure from the data? Is there a feature in the package? You can just call it?
Yeah. So literally everything is kind of it's split up into lots of different classes. So there's a structure learning class, there's a probability fitting class, and there's an inference class. And basically kind of you just step through. There's a load of notebooks on read the docs where you can just get some examples as well. But yeah, it's designed to be as similar to sklearn as possible, where you can basically just do dot fit to try get your structure to basically try fit the structure stuff. Similarly for the the probability fitting, right? Tries to keep it as familiar as possible to what people will be used to working with in their if they're using sklearn and things like this.
Yeah. I think we are pretty much close to 7 o'clock. Just one question and want to understand your thoughts. From your experience, what do you see in Bayesian networks and also causal inference domain? Where are they heading to? What is next for these domains? Are there any specific problems that most of the research scientists have to solve, and what are the key areas people are actually working on?
So I mean, everyone keeps trying to getting closer and closer and closer to ways to try and identify causation from the data. And it's obviously, it's not true causation, but there's lots of relatively new sort of exploratory data analysis techniques that kind of try and understand the relationships between variables and try and infer the causal direction. That is actively being worked on. There's stuff outside. I mean, from a Bayesian network perspective, I think the dynamic Bayesian network side is the least well researched so far, and sort of as you mentioned earlier, a lot of data can be time series data, and so I think DBNs is an obvious place to go. There's also lots of Bayesian networks is just one school of thought within causal inference, and this is the one that's basically pushed and propagated by Judea Pearl, the guy that invented Bayesian networks. There's a whole other school of thought which come up by a guy called Donald Rubin, and this is sort of Potential outcome framework is essentially the name that's given to it. Both two very active research areas. I think there's probably a lot more going on potential outcomes at the minute than there is on Bayesian networks, and probably that's the more frequentist approach, whereas Perl is the more Bayesian approach. So kind of yeah, maybe some more work on potential outcomes, maybe some more stuff on DBNs, maybe some more stuff on trying to infer the causal direction or causal relationship from observational data. But I think the last one is, yeah, tricky. I mean, they're all tricky, but like the last one in particular is very tricky.
Thanks, Paul. Thank you so much, Paul. It was very insightful seminar, and I think I believe most of the audience had a good introduction session, and they felt this session is very interesting, and I can see from some of the comments as well. We are thrilled to have you, Paul. And please do remember to send the answers to the 2 giveaway questions to octave@keys.com before end of the day tomorrow. Then the winner will be selected at random from correct responses, and will receive a gift sponsored by Microsoft. The winner will be announced at the next webinar series. Next webinar, production ready practices, on 15th of December 2020. So that will be on Tuesday, with Duminda Jayatilak and Nayur Khan. It will be a really interesting session from Duminda and Nayur. So hope to see you there. And before just wind up, please fill the feedback form at the link, and the link to the form is given in the chat box. The link is given in the chat box. So please fill the feedback form too. Thank you so much for everyone. Have a pleasant night. Thanks.